All right, so we're going to do some estimations and we're going to look at how this affects in physics. So the first thing I'm going to do, of course, is I'm going to share my screen and we're going to do a quick PowerPoint to kind of walk through this. So I'm going to start this PowerPoint presentation. So let's talk about estimates and rules of thumb. So one of the best tools that you have in physics will help you to determine whether or not you're on the right track for solving a problem is your own personal experience. Physics does relate to those things that we encounter every day. And one of the things I like to say is you're going to do more physics in your head than you'll ever be able to write down on a piece of paper. So we're going to look at how rules of thumb and estimations are going to help us give us a gauge of, are we on the right track? For example, we're going to be dealing with problems dealing with motion. This will include solving for time, for velocity, and acceleration. So let's take an example. And this is an example that most of us are very, very familiar with. We're going to travel from Oklahoma City, or travel to Oklahoma City from Tulsa, and it's going to take you about 125 minutes. The distance that you've traveled is approximately 110 miles. So which of the following is correct for an average speed? Now, this is a problem you've done in your head. You've done it as a little kid. You've done it in mathematics. You've done it in college algebra. You figured this out. Now, one of the things you're going to ultimately have to do is maybe you have to do a little bit of a conversion, but several of us have made this trip often enough that we can probably tell you, hey, all of those answers kind of look right, but I've traveled over 2 hours. So I know that if I traveled over 2 hours, that says I've gone over 120 miles if I'm doing 60 miles. So I know I've got to go below the 60-mile mark. So 60 miles per hour mark. So it's probably going to be 57 or 53. Some of you may take a calculator and you go, hey, that's a little slow because I know the turnpike, So you probably are going to come up with 53 miles per hour is a likely candidate to be correct. But you were able to eliminate a couple of those answers very quickly because you were able to do that. And your prior knowledge allowed you to do that with. So additionally, based on your experience, you can review data, and we see data all the time. We get that data in the news, we get data, we see a lot of those things. And so we want to know whether or not it sounds reasonable or correct. So let's look at some of these statements. Joe was able to walk 10 miles to the next town after his car broke down in 3 hours. Well, that's saying that if I go 10 miles in 3 hours, I have to be walking at a speed of a little better than 3 miles per hour. And a person can do a mile in about 15 minutes at a pretty leisurely pace. So that statement's probably correct. And we can look at, say, Sarah's longest jump in the long jump, which allowed her to win the meet, was 6.5 meters. Well, we got to kind of have an idea of how big 6.5 meters is, and that might be reasonable, that distance. An automobile was accelerated from a stop at a rate of 10 meters per second to achieve a final speed of 27 meters per second in 10 seconds. Well, this one might be a little harder. First of all, we're dealing in units we're not familiar with. 27 meters per second is actually about 60 miles per hour. And so if we're going to get to 60 miles per hour in 10 seconds, is that acceleration enough to get us there? We might actually have to put pen to paper on that one. Another estimate is you've said that an average person's heart will perform 115,200 compressions or beats in a 24-hour period. Well, you got to know a little bit more information about this. So if I have a resting heart rate of 75 beats per minute, I've got to do the conversion of number of minutes in a 24-hour period, and I've got to be able to make that estimation. Sure enough, that looks like a reasonable number. So we want to look at it. And then we can look at this if somebody were to make the statement, a quarterback's longest throw, I obviously got the wrong throw in there, in the game was 230 yards. We know that that's probably not right because the average football field is not over 200 yards. So we know immediately that this number's not in the ballpark. So we have a way to do a bit of checks and balances. So I'm going to give us another example that we want to look at because that balance will allow us to make comparisons. So which is longer, 12 inches or 254 centimeters. Now, a lot of us are going to have some conversion factors built into our heads. I happen to have the one for centimeters to inches built into my head, and I recommend that everybody does because it's 2.54 centimeters per inch. So if I have 254 centimeters, that's 10 centimeters or 10 inches. I know that 12 inches is going to be longer than the 2.5 or than the 254 centimeters. Which is longer, 30 days or 2,500 hours? Well, I'm going to have to maybe do a little bit of a calculation, but I'm going to find out that 2,500 hours is longer than 30 days. And which is longer, 50 meters or 50 yards? Well, we know that a meter is like 39 inches and a yard is 36 inches. So we know that 50 meters is going to be longer than 50 yards. So again, this is going to provide you with a check in your work. It also will allow you to fact check a lot of statements. So let's make a fact check on this statement. There are more atoms in a teaspoon of water than there are teaspoons in the Atlantic Ocean. Well, this is going to require us to do some more deep of a dive in our estimation, and this is going to be like more of the types of problems that you're going to get in this first chapter. So let's start with the statement. There are more atoms in a teaspoon of water than there are teaspoons in the Atlantic Ocean. Well, first of all, I'm going to have some information. I need to know what's the volume of a teaspoon, and I need to know what the volume of the Atlantic Ocean is. Now, for some of us, we may be able to get that teaspoon estimate pretty quickly because we cook in the kitchen and we make conversion factors all the time. So I happen to know that there are 5 milliliters to a teaspoon. So I can convert back and forth between the metric system that's going to allow us to get there. And we need to be in milliliters because some of the information we're going to have to use, we're going to have to go back to our chemistry thinking in order to be able to get that. But volume of the Atlantic Ocean, I'm probably going to have to look that up. So let's look at it. There are 5 milliliters in a teaspoon. And according to the National Oceanic Atmospheric Administration, the volume of the Atlantic Ocean is 310,400,000 cubic kilometers. Well, this is going to require us to do some conversions and to get some more estimates. So we're going to have to do some conversions and some estimating. So first, let's do the number of atoms in a teaspoon. That's a little easier for us. Most of us have taken chemistry, so we've got that kind of a handle on that particular conversion. We will have to make the assumption that all of the atoms in the teaspoon are associated with water. And that's just what we're going to make that assumption. We know that the density of water is 1 gram per milliliter. This is one of those MacGyver type things that you can think about, that you'd have it in practice. And this means that 5 milliliters is going to be 5 grams of water. To find the number of atoms, we're going to have to determine the number of moles of water and use Avogadro's number to determine the number of atoms. For water, there are 18 grams per mole, and there are 3 atoms per molecule. So practice the conversion, and you're going to find that there are 5.02 times 10 to the 23rd atoms in a teaspoon. Not quite a mole of atoms, but we can actually get in there and get it, so we can look at that. But now let's do that same type of analysis for the number of teaspoons in the ocean. We're going to have to look up a couple of conversion factors. For example, 1 milliliter is 1 cubic centimeter, and I'm going to use the difference between the notations here just to get you familiar that a cc is a cubic centimeter, and I'm going to show you that cubic centimeter notation there. 1 cubic kilometer is equal to 1 times 10 to the 15 cubic centimeters. So taking that big number that we got from NOAA and converting it into cubic centimeters, we're going to find that we get 3.014 times 10 to the 23rd cubic centimeters. Now we got to convert that into teaspoons. So we got to go back to our 5 milliliters in a teaspoon. And since 1 milliliter is a cc, we got to divide by 5 in order to calculate the number of teaspoons in the Atlantic Ocean. And we find out that it's 6.2 times 10 to the 8 times 10 to the 22nd teaspoons in the Atlantic Ocean. So we've got 10 to the 22nd, and now we do the comparison. We found that there were 5.02 times 10 to the 23rd atoms in a teaspoon, and we found that there were 6.02 times 10 to the 22nd teaspoons in the Atlantic Ocean. We actually determined that the statement is correct. So when you're doing these conversions, you're going to have to do these conversions and estimations. You're going to have to kind of do some things. You've got to figure out A, what's reasonable. B, you may have to look up some conversion factors. And C, you may have to actually come up with some numbers or some estimates that make reasonable sense. You're going to look at this, and this is going to really help you and give you a foundation in the physics, because that's what's going to allow you to be able to determine, does my answer make sense? And that's one of the first things that we have to look at. The other part of things we're going to look at is, do the units make sense? So we want to kind of keep those things together. Hopefully this will help you, and this will get you into your homework.